What's up, guys? Long time no see. I've been out for a while because I've been busy working on some academic activities, and I thought I would come up with a new update, which would come in form of a presentation that I presented to the department at my school. So I hope you guys enjoy it, and of course, I hope you learned something new. So, dear viewers and listeners of this lecture, and of course my colleagues from the department, I would like to present my topic of both my diploma thesis and my upcoming dissertation, called Implicit Representations and Evolving Surface Remeshing on Polygonal Meshes. As for a more gentle introduction to the pretty extensive topic, we first demystify the notions already present in the title. For computer graphics applications, objects on the scene have different representations, depending, of course, on the data they're constructed from and the resulting format specifications, 3D printing or various other applications. Implicit or functional representations essentially assign a value to a given region in space. In their simple examples, they can take form of continuous or even smooth functions of multiple spatial variables, such as this 2D quadratic form centered at the origin. Its level sets are, as you can see, concentric circles. These simple scalar fields can be combined using various operators to give rise to more complicated objects. The most widespread representation of objects in computer graphics is the polygonal mesh representation, in which the real-world or fictional objects are represented using polygons formed by connecting vertices in Euclidean space. We can then modify such geometries, providing them with texture information or changing their topology, for example, vertices and their connectivity. As you can probably guess, both of these representations are relevant for different applications. For example, most video game models are simple animated polygonal meshes with textures trying to save as much storage space as possible. Other, more exotic objects on the scene may be represented by fields under a given resolution. We can then choose to render a given set of contour surfaces by polygonizing a level set with some constant values, using, for example, the marching cubes algorithm, which gives rise to an interesting way of creating organic membrane shapes. A proper multi-purpose geometry engine would then allow the user to control the quality of the created meshes. All of these stages are, of course, interconnected and can be combined in various ways. As a matter of fact, this wide range of possibilities gave rise to some of my passion projects that I worked on. Here you can see an organic figure shape being modeled from implicit fields generated by simple geometric primitives like spheres, boxes, or cylinders. Combining the overall influence of individual fields creates this golem-like figure after a chosen level set is rendered by the marching cubes algorithm. Now, as is usually the case, things can get pretty complicated when you introduce more complexity into your scene or into the generating geometries. And as I mentioned before, you may also want to control the topological or overall geometric properties of your meshes, so that they not only look better, but also take less storage space and are faster to render. That being said, I'd like to outline a rough timeline of this project. Clearly, I won't list all the things that I've ever done research on. The purpose of this presentation is to focus on this particular project, which, as the title says, attempts to bridge implicit and polygonal representations of objects by being able to efficiently transform one representation to another, and then use the implicit representation in particular to serve as a buffer for an evolution-based process, which I'll specify later on. This process is hypothesized to create a new mesh with a desired quality. It all started with the implementation of the so-called meta-object. The goal of this project was to implement a tool for generating implicit scalar fields from geometric objects on the scene. While it was relatively simple to do this for geometric primitives such as spheres, cylinders, boxes, etc., and account for the transformations and combinations of individual fields, the first real challenge was to do this for general meshes. The idea was to be able to compute a distance field from any given mesh object, regardless of its polygon count. The brute force approach was far too slow for any real use, so accelerative approaches were needed. After a while, my solution stabilized on using 3 successive steps, starting with a bounding volume hierarchy searching, while using an octree for regular space partitioning, followed by the so-called fast sweeping algorithm, which is a type of iconal solver that runs in linear time. I did this in parallel with the first part of my diploma thesis project, the goal of which was to implement a polygonal remeshing framework using a kind of shrink-wrapping approach, which actually needed a distance field to a target mesh. Now, as it turns out, shrink-wrapping, especially using the kind of model I used, is generally bad at wrapping onto the target object in highly non-convex regions, like between or under the ears of the Stanford bunny model in the animation. In fact, even slight model concavities lead to the stretching of mesh triangles, which hardly converges to an optimal mesh solution. So after a few months' break, I returned to academia, revisiting the old problem. From the experience I gained as a C++ developer, I decided to completely refactor the old code from my diploma thesis. Earlier this year, the project, previously called Surface Evolver, started its transformation to a new app, Symplectus, the geometry analyzer. The primary objective of Symplectus is, of course, to be able to better solve the problems that I tackled in my diploma thesis, and of course many other applications that will arise in the future. As of today, I've covered additional topics with my PhD supervisor, such as mesh topology adjustments, where they're really needed in highly concave regions during surface fitting, better tangential adjustments to mesh vertices from an even older model from as early as 2002, widely used for computing brain shape extraction using a sort of icosahedral sphere mesh evolving into a desired shape, plus alternative evolution surface varying models such as Wilmore flow, and of course, in the last 2 work-in-progress items, I cover improvements to the bounding volume tree for intersection and nearest primitive search queries, which I plan to conclude by writing a comparison of methods article. In the first part of this lecture, I'd like to introduce the viewers to the notion of signed distance fields. If we denote a surface as a subset of the 3D space by capital gamma, the unsigned distance function to gamma is defined at each point x in space as the distance to the closest point on the surface gamma. The signed variant of the distance function is multiplied by a sign factor, which is an indicator which equals -1 if the point is in the interior of a closed surface and +1 elsewhere. These spatial geometric objects are an essential tool for geometric modeling and simulation because they extend the definition of surfaces into the 3rd dimension. Much like force fields in physics, distance fields form a basis for object-to-object interaction. In their simplest form, a signed distance field serves as a spatial indicator of whether a given point is inside or outside of an object. Such indication is crucial for physics simulation and a variety of other applications. Unless we use simple objects with clearly analytically defined implicit distance functions, distance fields take form of values stored in a grid. Much like images contain values in pixels, general scalar grids in space have values assigned to grid points, corresponding to regular regions of space, voxels. The contour surfaces of such scalar fields can be generated either using one of the many variants of the Marching cubes algorithm or a custom voxel polygonization technique. For the Marching cubes polygonizer, I used the original model optimized by Paul Bork, using these lookup tables that encode all 256 surface intersections with the cube's edges, which then get mapped onto a particular triangulation. For some Minecraft-like renderings, some users might prefer a voxelized contour. Most online implementations I've found, however, have really bad performance, so I applied the ideas from Paul Bork's implementation for the much less numerous combinations of quad-voxel walls approximating a contour surface. The distance fields of geometric primitives such as a 2D or 3D box centered at the origin are easy to compute using closed-form expressions. Their transformed versions are also easily computed by evaluating them at inverse transformed grid points. A typical problem that needs to be solved when working with such primitive scalar fields is the scaling problem. The transformed object may be scaled and thus create a very visible distortion of the sampling grid. This is specifically problematic for unequal scaling. One way to solve this for geometric primitives is to extract the scaling component from the transformation and use it for adjusting primitive parameters. For example, instead of letting the scalar field of this box primitive stretch in the x direction, a scale factor can be added to the box length in this direction. Since distance fields are increasing functions, we may be tempted to combine multiple generated fields by simply adding them together. If we do so, however, we create a region of constant value right between the field primitives, which does not look natural when rendering the contours. We could either take the maximum value of two increasing distances, essentially doing a set union of regions below primitive distance contours, or we can use a form of inverse square law, which automatically allows us to add the distance fields, producing a superposition of fields at every point. There are, of course, many ways to do this, many of which are mentioned in Chapter 5 of Matthew Sanchez's 2011 thesis. Computing a distance field to the closest point on an arbitrary triangle in space is among the more complicated calculations of primitive distances. The space around the triangle is divided into as many as 3 vertex regions, 3 edge regions, and 2 above and below plane regions, giving the total of 8 regions, each with a unique conditional expression. The user can then compute such distance fields from individual triangles, or alternatively, their edges and vertices. Combining many triangles into a single mesh object that would generate a distance field would mean that at each sample point, distance to every mesh triangle needs to be computed, and then either combining them into a superposition blob, which wouldn't look good, or taking their set union, or comparing them until the smallest distance is found. The overall number of operations slows any real-time updating to a state that's far beyond user-friendly. Updating a scalar grid of 100 cubed voxels containing a 10,000 triangle mesh implies 10 billion floating point comparison if-else operations. Running such brute force computations on regular machines results in application freezes for several minutes. This was more than a sufficient motivation to use some sort of accelerating structure for reducing the total number of triangles compared to a single point. My algorithm for accelerated computation of signed distance fields to polygonal meshes is actually a combination of multiple approaches. The input data is a set of independent triangles without any constraints on closed or manifold surfaces. In other words, those we can uniquely measure with a local coordinate map everywhere. And of course, an offset value for expanding the original mesh's bounding box. First, an AABB tree is constructed from the set of triangles referred to as the triangle soup. Then, we use the search tree for recursively subdividing regular volumes of space, cubes, whenever they intersect a mesh polygon, terminating when minimum voxel size is reached. This spatial data structure is referred to as octree because it subdivides each cell into 8 children when required. A rectilinear grid object covering the surrounding space is created and expanded by a sufficient offset. It is first initialized with a numerical infinity everywhere, and then the computed exact distance is stored at the octree leaf voxel centroid positions, coinciding with a subset of grid voxels with which the surface intersects. Afterwards, the iconal fast-sweeping algorithm is called onto the scalar grid initial data, and after 8 sweeps in each direction, it fills the region with a numerical solution. An optional step for closed surface meshes, or meshes with very small holes, smaller than voxel resolution, is to compute the sign of the distance field by flood filling the entire grid volume. The AABB, or axis-aligned bounding box tree, is a spatial data structure, a binary tree in particular, that allows us to search for mesh-to-mesh or mesh-to-box intersections, as well as closest primitive to a given point. This all happens in O log n on average and On worst case time. The key fact is that unlike for the so-called KD tree, the geometric data is stored in the tree leaves only, and in order to get from the root volume node to the leaf, the tree needs to be traversed all the way down. My thesis app did not have any balanced implementations, so the leaves are not necessarily of the same depth. The tree construction takes place recursively, while splitting each node until it satisfies some sort of leaf conditions, such that the total number of primitives, triangles, is greater than 2, or that there is no great imbalance between left and right child node candidates before splitting. It should be noted that bounding boxes can easily share triangles which overlap with multiple volumes. As for the splitting procedure, this is the largest bottleneck for tree construction in general, while at the same time it requires us to sort the node primitives properly so that there's as little imbalance as possible, and a cost function is evaluated for multiple split position candidates, which considers future child node bounding box relative surface areas weighed by triangle counts on the left and right side. If we sample the cost function in 8 locations, we can then do all the comparisons in parallel on 256-bit SIMD, or single input multiple data registers, using C++ intrinsics. In fact, according to Hunt, Mark, and Stoll, rather than sampling it evenly across the interval along split axis, it is better to resample the cost function so that it's most concentrated in regions where it changes the most. That's where the local minimum is likely to be. Another key thing to consider is that unless the triangles intersect the node's bounding volume, they are not present in the node. Now, what I first thought to be a bug rather than a feature was that my implementation did not use any additional nearest neighbor search subroutine. When you're looking for the closest primitive and you only consider the node with the closest bounding volume to the queried point, you're likely to run into a situation, as in the image, where you finish the search by not actually finding the closest primitive to a point. As you sample the space beyond the bounding volume with closely packed primitives, there is a sudden discontinuity in the field. This is precisely what we see in the contour plot of a high-resolution distance field around the Stanford Bunny model, computed by the closest point without nearest neighbor search queries. Fortunately, this is not what happens for box primitive intersection queries for small box volumes. which meant that creating a sort of voxelized outline of the mesh geometry in space was relatively fast, and with coarser grids, the solution converged to a real shape. Besides the nearest neighbor search, my implementation needed additional optimizations. According to some sources in the game dev community, storing tree nodes in an array and traversing this array during query is faster, but harder to implement. This tree implementation is sometimes referred to as iterative, while the former, constructed by recursive allocation of nodes, is of course recursive. I wanted to compare the effects of these two radically different implementations. After more than a year of gaining some industry experience, some object-oriented design patterns rubbed off on me. Instead of implementing a dependency for each implementation, I designed the following bridge pattern. As you can see, there are two main interfaces unifying both iterative and recursive implementations of the binary tree and its nodes. In the implementation context, binary tree nodes need to know whether they are a part of a recursive or iterative implementation and behave accordingly. However, each abstract node has a query data node, which serves as a shadow node in the external context, containing the actual data and its implementations, such as the AABB node or KD node. In fact, they implement all the data handling and querying utilities necessary for searching and construction of the AABB tree and KD tree respectively, without accumulating too much functionality into a single node type. Another very useful implementation that's currently underway is the self-balancing property of binary trees during construction by node rotation. The type of tree we see in the animation is called an AVL tree. I've chosen the mesh octree for partitioning the space around the mesh object into regular volumes. The subdivision is relatively simple. Split each volume into 8 subvolumes and only keep those that intersect the mesh. The box mesh intersection query happens in logarithmic time thanks to the previously constructed AABB tree. For leaf nodes, the actual distance to the closest primitive from the voxel centroid is computed. The precise distances sampled at octree leaf cube centroid points get mapped into the index space of a scalar grid. As I mentioned, the scalar grid is initialized with a very large number value everywhere, so that no distance value is ever larger than this value. With the non-infinite exact values assigned to cells outlining the mesh surface, this serves as an initial condition for the fast-sweeping algorithm that iterates across the entire grid 8 times and completes the rest of the distance field. Since the distance function to a set gamma is the solution to the Eikonal equation with unit right-hand side and a zero Dirichlet boundary condition on the generating set gamma, the fast-sweeping algorithm requiring 2 to the power of n sweeps, which is 4 in 2D and 8 in 3D space, fills the rest of the scalar grid with numerically closed distance values. Now, the reason why the algorithm sweeps in different direction each time lies in the numerical method itself. Since the Eikonal equation is a nonlinear hyperbolic partial differential equation with the behavior along its characteristics, the black lines emanating from gamma on the image, defined by the right-hand side of the equation, it should only be updated if we iterate along the direction of a characteristic at a given point. Locally, new values are computed only when neighboring values in the iteration direction are increasing. To avoid working with infinities, a minimum neighboring value is considered. The numerical infinities then denote areas that have not yet been covered by any sweep iteration. For updating each cell, this translates to solving a quadratic equation for the new cell value, which corresponds to the farthest intersection of a circle with the identity line, y equals x. The coordinates of the circle's center are determined by the relevant neighboring cell values. As you can see, the sweeping completes the entire field in linear time, correcting the values upon each sweep so that they satisfy the characteristic property of iconal equations, which is, in the case of distance function, a unit speed increase away from the generating set gamma along the characteristics. For basic applications of the distance fields, we can finish with fast sweeping. But for some, we may also need to distinguish the interior and exterior regions of a closed surface by computing a sign function, which determines whether we are inside or outside of an object. The image on the left shows that a meta-object from this bunny mesh does not need to be hollow. We don't need to keep all the triangles from the inner layer since we can't even see them. One approach is to use a flood filling algorithm which spreads a state from a seeding pixel or voxel across the entire field, much like the paint bucket tool in MS Paint. This, of course, happens recursively and uses the STL stack container, which is generally slow to work with. So, obviously, this last step is the bottleneck for scalar grids with large resolution. Now let's conclude the first part of this lecture by listing the average computation times in seconds for the Stanford bunny model for various grid resolutions. As you can see, the signed computation column has the greatest contribution to overall time for larger grids. In the animations below, we see the meta object with geometric primitives as well as the Stanford bunny model. Clearly, there is a lot of space for performance improvement, which is precisely what my current line of research is about. I'm implementing a robust framework to test multiple approaches and their combinations on a large dataset of 3D models. The second part of this lecture will focus on the key topic in my diploma thesis: evolving surfaces driven by an advection term. The original idea was to shrink fit a mesh of higher quality onto a mesh of lower quality. But as it turns out, such physics-based simulation techniques do not produce surfaces with high-quality polygons, because the polygons are stretched in the non-convex regions of the target mesh. Multiple techniques of tangential vertex redistribution were used, but were still unable to solve the polygon stretching problem. Although originally used by the math department at the Faculty of Civil Engineering in Bratislava for 3D image segmentation, my colleagues later used the shrink wrapping evolution techniques for constructing mesh geometries from point cloud data. Around the same time these methods were researched on my major, Zocht and colleagues published a Z-graph paper which used repeated shrink wrapping of a mesh with decimation techniques to produce so-called nested cages. The idea of remeshing using a process referred to as shrink wrapping dates back as far as to 1999. Now, because different institutions use different terminology for this process, the information about shrink wrapping came under my radar only recently. The colleagues under my master's thesis supervisor, Professor Mikula at the Faculty of Civil Engineering, used the following advection diffusion model with the negative gradient of the distance field affecting the advection. The fundamental component of their model is a diffusion-based type of flow, represented by a partial differential equation that can take place on the entire spatial domain, where a scalar field is defined, or on mesh vertices, only involving a single surface rather than all level sets. The animation on the left shows a repeatedly applied curvature filter on a 2D image, dissipating all features with high curvature faster than the rest of the image. The flow on the left depicts a triangular mesh surface contracting under a mesh-based Lagrangian mean curvature flow. The solution to the parabolic flow equation is an immersion of the surface into Euclidean space at each time. Immersions are maps between smooth manifolds that preserve the injectivity of the differential. In other words, if we immerse an abstract manifold into a higher dimensional ambient space, the immersion is allowed to have self-intersections, but tangent vectors on two distinct points cannot map onto the same vector. Professor Mikula and colleagues formulated the evolving surface problem in the following fashion, decomposing the flow velocity into a normal and tangential part with a given initial surface immersion. The definition of curvature needs to be intrinsic to the immersed surface. We can think of mean curvature as the sum of principal curvatures, which are actually reciprocal radii of an osculating ellipsoid at each point. The parabolic equation's right-hand side can either have the negative curvature vector or be represented by the Laplace-Beltrami operator, a sort of intrinsic Laplacian with second derivatives encoded in the surface metric. This type of flow is referred to as mean curvature flow, and only a handful of exact solutions to this equation exist. I mentioned that mean curvature is the sum of inverse radii of the osculating ellipsoid, which means that if the osculating ellipsoid at each point is a sphere, the whole surface is a sphere. This means that the mean curvature turns into the sum of two identical inverted radii with a minus sign, leading to a simple ordinary differential equation for the radius. Given an initial condition, the starting radius r0, the solution is a shrinking sphere, whose shrinking rate actually approaches infinity as radius approaches 0. As a matter of fact, any closed surface loses its local features with high curvature, attaining a sphere shape, which then shrinks to a point. This result was actually shown for this type of flow in 1992. So, from what we know now, the evolution model consists of mean curvature flow and some advection term, which is just made of a unit normal to the immersed surface, f, multiplied by a control function eta. Both control functions, epsilon and eta, are functions of the Euclidean distance to the reference at gamma, the target surface. Control function eta has the most control for points sufficiently far away from the target mesh, and the dot product terms actually rotate the surface normal so that it coincides with the distance gradient. In the animations below, we see different effects of the advection term when setting the control constant d as 0 on the left, and when both constants equal 1 on the right. The main difference lies in the fact that mere projection along surface normal makes the surface stuck when the distance gradient is perpendicular to surface normal. This leads to membranes stretched over a concave region which actually converge to surface patches with minimal curvature. If we consider both terms, the surface rotates in space so that its normal coincides with the distance gradient. By looking at what the dot product terms in function eta actually represent, we can write the theta term down as a rotation in the negative distance gradient direction, with the angle alpha being an angle between the surface unit normal and unit distance field gradient. This is, however, still not enough for the triangles which are often prone to excessive stretching in non-convex regions. The overall algorithm is outlined on this slide. We start with a mesh, capital X with stripe, preferably of higher quality, like an icosahedron sphere mesh, for example. Also a target mesh, capital gamma, time step tau, and the total number of time steps nt. Of course, an implicit representation of target mesh, capital gamma, needs to be computed within some bounds. Also, this bounding volume is meant to contain the evolving solution, in case it explodes due to numerical instabilities. For each time step, we compute the surface properties such as normals and so-called co-volumes, used as finite volumes in a finite volume formulation of the evolution system. Each mesh vertex has a ring neighborhood of adjacent triangles. There, the covolume represents a union of subregions of adjacent faces, with a sampling point as the triangle barycenter. The solution is obtained for each time step by solving a sparse linear system derived from the parabolic flow equation. The curvature terms contain a cotangent formulation of the mesh Laplacian, the Laplace-Beltrami operator, derived in a 2003 paper by Meyer, Desbrun, Schroeder, and Barr. The finite volume formulation of the problem, with some alternative approaches, is dealt with in a 2019 paper by Tomek and Mikula. We follow by solving the linear system using either the SOR, successive over-relaxation method, or BiCG-STAB, the stabilized biconjugate gradient solver, for 3 coordinates of each mesh vertex. The mesh solution is then checked and updated. Mikula and colleagues introduced a series of tangential redistributions for better control of local vertex density and polygon orientation by not allowing mesh vertices to clump together in regions with stronger curvature flow. The most complicated type of redistribution is the volume-based tangential redistribution, which relies on defining a kind of redistribution potential, psi, on the surface immersion and transforming its gradient in the immersion matrix into a tangential velocity vector defined at each vertex. This means that an elliptic equation for the unknown potential psi needs to be solved for each time step on top of the 3 linear systems for vertex update. The key contribution of this redistribution is that it makes sure that the volume element evolution is asymptotically uniform over time. A simpler version of redistribution is angle-based redistribution, influenced by angles in the vertex 1 ring neighborhood, such that the angles are adjacent to the central vertex. The results were satisfactory for curvature flow simulations and for shrink wrapping of relatively simple non-convex target meshes. The bunny model, however, exhibits a high degree of triangle stretching under and between the ears, regardless of the redistribution type. The shrink wrapping of the bust of Max Planck model produces satisfactory results because it does not have any sharp features like bunny ears, where strong triangle stretching or pinching could take place. For smaller subdivisions, however, the numerical method becomes unstable, often exploding when the covolume areas drop below the time step length. So, all things considered, the new insights found in this project were a robust sign distance field computation algorithm for polygon soup meshes, an implicit field generator with marching cubes and voxel polygonization, Lagrangian mean curvature flow shrink wrapper of triangular meshes to polygon target meshes, and a binary tree implementation to query data bridge pattern. Now, the question that remains is, what's next? What is my plan for the upcoming future? Well, I might have more than a few things on my list, so let's take a brief look into them, shall we? The current design of the Simplectus app looks like this. It sort of resembles a layered architecture pattern, but only partly because, for instance, the input-output services will be prone to massive changes in the future. The Surface Evolver app had a Qt-VTK branch where the front-end part was done in Qt, and the 3D viewer used the VTK, a visualization toolkit library, which runs on OpenGL. I might want to revisit this solution in the future, but we'll see. The kernel for numerical computations, meaning solving large linear systems in parallel, might require some third-party library, for example, Eigen. Also, I might want to compare the results with a third-party framework such as CGAL or Leda. The only current third-party library is the Google Test Framework for C++ unit testing. Although it takes a lot of time to cover all the test scenarios, this is, as I found along the way, the most efficient way to implement and test many components that do not have to interact yet with the incomplete app. So, after finishing the work in progress items from the list in the beginning of this presentation, I'll move on to finalize the command line input-output nature of my app. The command framework is supposed to work much like Git with basic commands on geometric files such as .obj, also allowing the user to chain the output from one step to another via a shell-like pipeline operator. This will require some additional architecture proposed in the diagram below. Furthermore, a lot of mesh data needs to be tested and a robust performance measurement needs to be implemented, not just using std chrono calls before and after some code. Since Simplectus is meant to be a tool for mainly academic use, it needs to be supported on multiple operating systems, especially Linux. Most C++ code does not care whether you run it on Linux or Windows, and the CMake system allows the user to generate project files under most platforms. However, some basic, for example, error handling utilities need to be done without using headers, specific for Windows. After all of the fundamental components of the app are functional, more functionality will be added in the surface shrink wrapping functionality. The numerically unstable models should be replaced by simpler, more stable ones. And what works for triangles should also work for quads. Then, in the next phase, Simplectus should grow into a GUI version, using a Qt frontend and VTK for visualizing the 3D content. Afterwards, some demos recreating the meta object with additional features, as well as more surface evolution demos in the new GUI version, should be implemented and tested. At this point, it will be time to move on to some new topics introduced to me by my PhD supervisor. For example, the hybrid functional representation, or HFREP, of 3D objects, and view-based and data-based retriangulation of polygonal meshes on the scene. I'd like to conclude my lecture by expressing gratitude, mainly to my current PhD supervisor, Andrej Ferko, and Robert Bohdal, for regularly taking time to discuss this project with me and introduce me to new ideas upon every opportunity. Then to Professor Mikula for supervising my diploma thesis, Lukasz Tomek for being an opponent to my diploma thesis, and more colleagues from the Faculty of Civil Engineering like Balázs Kósa for advising me on the implementation of the fast sweeping algorithm, and Peter Sarkozy for answering some more theoretical questions in differential geometry. Last but not least, I'd like to give thanks to my former colleagues at Vektari and my current colleagues at Němeček Alplan for providing me with an environment for learning true industry experience and workflow. And finally, I'd like to send gratitude to all of you, the viewers of this lecture, for finding the time to listen to it in all its intricacy. So, I hope you learned something new, and see you next time.